That document will tell you all you need to know about the project. So it's this one right here. And there are a couple of things, there are a couple of words now that you will recognize in that document. So you're going to get in groups of 4 students, and the idea is come up with a few ideas of some sort of engineering problem that you don't know the answer to, that is non-obvious. And you're going to use the techniques we learned in class here, the design of experiments, to design a set of experiments and then execute the experiments, and then you'll complete a few deliverables. So the experimental design has to be one of those things. So this is what we've been talking about now. We've been doing full factorials. We'll talk about center points in a day or two. So that type of design is something you could pull together now. There are other ones that we haven't got to yet, but it's not too early to start forming your groups and start thinking of the problem that you would like to explore. You can use our equipment in the lab if you like. I don't mind if you tie it in to another course that you're taking, so it could be part of a lab. It doesn't bother me as long as your other instructor's okay with it to tie those things together, or it could be something completely separate. So the 3 deliverables are, once you think you have a project, what you need to do is give me your ideas for a project, and do that before the first deliverable. I think this is the one that's due on the 13th. And in my email I mentioned, we're going to have about 9 groups. So that means not all 9 groups are going to meet with me on the 13th. So figure about the week prior to the 13th being ready for a meeting. And once you have formed a group, you can send me a meeting request and get on my calendar. It's going to be first come, first served. So if you wait, so here's the deal. If you wait, and then, so you wait until November 11th, and then you go to make a meeting request to me and find all the times are filled, and then you have to meet after that deadline, it's going to be late. And it's not going to be my fault, it's going to be your fault. So keep that in mind. So get your groups together, get your meeting request locked in. Sometimes things come up where I have to move things just because of all the other stuff I'm doing. In that case, if I have to move it past the deadline, it'll be okay. So before this meeting, you have to have a project approved. So you have to see me. It's more of an informal meeting at that point, but pitch a couple of your ideas that you have, and we can talk through those and pick one that will be useful. So what you don't want to do is you don't want to come to your preliminary meeting with a project that I haven't seen and have me say that's boring, it's uninteresting, it's not worth doing, and you're going to have to start over. So that happened last year. A group came and had a project idea that was lame, and I told them that it wasn't worth doing. But the happy side is they went back and then they got a really good project. So they had a really interesting project after that. But initially it wasn't something that was worth doing. So what I'm trying to say is approach this project of, okay, yeah, you got to do it for class, but have some interest in it too. That way maybe other people will be interested in it. It won't seem like such a chore. Don't just pick something of, okay, this is something easy that I can get done. So chances are, if that's the criteria you're using or criterion that you're using, it won't be very interesting. So pick something that at least has some personal interest to you. So the groups that have done that, it has been a lot more fun, a lot more interesting for everyone to listen to. And then it's a lot better when we're discussing real issues of the design. So then we're going to have a preliminary meeting, and you can read all about it in the document, all the things we have to do in the preliminary meeting. So all that's self-explanatory. And then after the preliminary meeting, then you're going to go out, collect your data, analyze your data, write a memo to me, and then you're going to give an oral presentation to myself and your classmates over your project. And that is going to be the project grade. All those parts, there are deadlines for each of these deliverables on the syllabus, and I've told you the first one. Just let me double check to make sure if I have the syllabus. Yeah. Yes, so Friday, November 13th, those have to be done. The preliminary meetings with me. So if you have any other questions, this document is pretty self-explanatory, pretty exhaustive. This is what I'm going to be using to grading your meetings. This is what I want in the memo report, and this is how I'm going to grade your memo report. This is how to give an oral presentation, and this is how I'm going to grade your oral presentation. So it's pretty straightforward. Most of the information is in there. Yes, Morgan?
Do you have examples of what people have done in the past?
I haven't saved examples. I would have to scrub all names and stuff out of those as well for violations. Oh, topics people have done in the past. So, so people have done things like, I'm trying to remember last year, they were looking at vibration, factors that influence vibration on the vertical mill in the shop, and they had, I think, 7 factors in a screening design there that was good. Another group did the spread of a shotgun blast, so that was last year. Someone who was a hunter was actually interested in that, one of the factors in that, so that was great because there's some personal interest in that. Some people did sort of airplane design, so they were somewhat interested in that. One group and 1 year had proposed the factors that influence the rate that water boils, which was boring and didn't get done because it was boring. What were other things? Other projects. We used to do more analysis of variance, so we had some ANOVA. One group did hardness testing of certain things, so that was one test. One group did strength of paper towels. They had to build their own test apparatus. So I don't know. They were really interested in paper towels, I guess, but at least it had something to do with strength. So, so anyway, it is fairly wide open. Some of them have projects that I said don't do, and they did, and they were disasters. And not that I can tell always if there's going to be disasters, but there was one group, it was a few years ago, that had something that was just extremely hard to measure, and they didn't have a good idea of factors, and and then they didn't do any analysis on it either, so it didn't turn out so well. So, but that was a few years ago. There are, I think I posted some project ideas on there as well. And it's not from me, it's this other professor, one of the guys that does a lot of design of experiments. I think he had like 101 project ideas that he ran in his class. One of those is the factors into boil water. So he may think it's a good project, I might not agree. So just because it's on that list doesn't mean it's something that I would say go ahead and do. But particularly if you have some interest, and it doesn't have to be, it has to be somewhat, engineering type stuff. But I'm really interested in something you're interested in. So yeah, one group they were shattering mugs. So they pitched as a properties of materials class. And so then they realized some interesting things that sometimes you need to do a little bit more research ahead of time before you start experiments if you're going to find anything useful. And so I guess that's discovery as well. All right, so start forming groups and think about interesting topics in which you could fulfill the requirements of the project, which means it would fit within these categories. So you'd have to have, if it's a full factorial you're shooting for, you have to have at least 4 real factors that are reasonable to test. So start thinking through that. And any questions on the project? If you have trouble getting in a group, or if just let me know, send me an email, and I can try to help put you in one. All right, so here's where we are today. We are wrapping up DOE 2. And parts A and B we've been doing for quite a while, and hopefully those were going well when you were doing them last class period. And if they're not going well, as I mentioned before, that's a signal where you should probably be spending some more time with this material before you get further behind, because this stuff should be there by now. Good to write that down right away. Good. Tell me what you got there. Okay, let's start over here. This average yield. Does anyone have a number for this? What was that? 44.5. What about this variance? Variance 43.0. Okay. 43.0. All right, what about the mean? What's that? What's this mean? 53.2. And then R, the sum product. Negative, 34.3. The effect, that divided by 4. 8.5? 8.6. And then T. Negative 3.1. So SP squared? 46.5. So square root of that. Patrick, what'd you get? 6.8. And SE. Who wants to do SE? Nicholas? 3.8, did you say? 2.8? Couple things. Degrees of freedom. How many degrees of freedom in this variance? 2. And all the way down. So total degrees of freedom is 16. Good. T star. What's alpha here? 5%. It's not given. So T of 0.025 and 16 is what? 2.12? Good. Very good. Okay. So we did that. What effects are significant? Temperature, residence time, pressure, residence time, interaction. Did you guys get those? Good. Let's look at B1. Show what I just did by inspection was perform these hypothesis tests. So it's good at least go through the formal procedure once. So for this, we would say the null hypothesis, the mean of the residence time effect, the mean value of ER, kind of lots of subscript, is 0. And the mean value for the effect of residence time is not 0. Then we assume H naught is true and draw our distribution, which this is the distribution of the effect. So that's the distribution of the effect of residence time, right? And so what's the noise there? Right, 2.8, or in symbols SE. So then we need to calculate the statistic of interest, which is going to be the effect of R minus the hypothesized effect divided by the noise. So ER was minus 8.6 over 2.8 minus 3.1. And we compared it to T star and found there's T star, negative T star, and our T value was there at minus 3.1. Yes, we're further out in the tails, so that's significant. So we reject the null hypothesis and accept the alternative hypothesis that the mean effect of residence time is not 0. In layman's terms, we say residence time is doing something. Residence time has an impact on our response, which is the yield of the reaction. Okay. So please don't lose track of that stuff from chapter 6. That's what we're doing.
Did you get 2.16?
The 2.12,
Oh, okay.
sorry, so is the C star there. Any questions on those parts? That's the review stuff from what we've done several times. And now some of the newer stuff that we're doing. Let's get rid of this. Move it down there. Model. Who has the model part done? I don't want to get too far ahead. All right, let's just wait. So given that, keep working on the other parts of the problem. And since we're taking a lot of time to look at the problem, give me some advanced forms problems. So F is how we determine You guys get that model? Good. Great. Is that what you guys all had questions? Great. So this is the model of just significant things, and we had the one little exception was here we have a significant interaction that has pressure and residence time. Therefore, I need to, let's put it in here, do this, and add the main effect of pressure to the model, which is going to be plus 0.92 over 2 times pressure. This is really messy. Okay, does that look right? Jeff?
Why would you replace that with 0? And, like, I don't have it in the equation, but why not replace instead of that 0.92 with 0? Because it should have been on this period.
I'm sorry, why not replace
0.92,
with?
why not just put it at 0?
Okay, why do we have this here? So,
I recognize the value of having P in the equation, because that's what you said.
yeah.
But
If the effect of 0, that's the same as saying P is not there. If the coefficient is 0. So was that your question?
why can't you just replace that with 0 since it's just noise?
Okay, since it's just noise, normally we would, but because of this, we include the main effect term. And if we include the main effect term, that coefficient can't be 0. Otherwise, it's not there. 0 times P would just be, it's just gone. So you've got the right concept that if it doesn't prove itself to be significant, normally we don't include it in the model. But it's just because there's this one exception. Okay, so that's our model. Now, we need to figure out temperature, pressure, residence time. So reaction yield, let's say we're trying to maximize the yield, which is what we're saying here. First, what's the easiest one to pick first, to set? Temperature, just a main effect. So that's positive. We want that to be big. Temperature should be a +1. What's the next one? So we got pressure and residence time. We want P to be positive? No. Why both negative? Right. This is saying P and R should be the same sign, right? So that's okay. And then this one is a lot bigger than P, so if we set R at -1, P should be also -1. Bless you. Okay. Another way to brute force that would be to put your model predictions here, and just then you could pick the biggest one of those numbers, and that's your maximum. But don't just pick the biggest one of these, because those are data points that have noise in them. So the model is supposed to account for the noise and smooth it out, if you will. Okay, now part E. Yeah, Matt.
So is it just coincidence that the biggest average yield matches the condition that we found?
Oh, good question. So Matt's question, is it just coincidence that that our model predicts the maximum yield that is the maximum, the largest of these? Yes and no. It doesn't always have to work out that way, but the model does come from the data, so very often it will agree.
So if we use it as a starting point?
I would say don't use it as a starting point, just because you might use it as an ending point at that point, which means that I wouldn't get in the habit of looking at picking the largest single data point and using that to guide you. Rather, the model includes all the data points. So I would go through it this way. Okay, the next question. Predict the yield at this optimum. So what we do, we put these values into our model. And R goes in there and there. And we predict a y hat. Anyone get that far? Anyone get a y hat? Yeah, Vaughn. 83.7. Anyone else get that? Good. 83.7. So plus 1, minus 1, minus 1. So that's run 2, right? And that's our data says 81.4, and our model would predict 83.7. So there's pretty good agreement between those two. Hooray. That's good. Any other questions on that part? Bonus round stuff. How would you check if it's a linear model? We will get to that today, so I'll defer that one in. But this one's not on the docket for today, so what's the power of this experimental design to detect an effect of 8 or more? So there, it's good that we started thinking about this in terms of hypothesis tests. So we're saying the mu of the effect is 0, and we found a T star, or let's just say an E star there. And alpha is 5%, so we have 2.5% there, 2.5% there. That's the test we're doing. That's the hypothesis test that we figured for one of them, and it's the same for all of them. We assume the mean is 0. The effect is doing nothing until our data proves otherwise, which means we get a T statistic that's in the tails outside of T star. I just drew it in terms of E star in this case. So anyway, everyone okay with conceptually that's the hypothesis test we're doing for every effect. When you look at the bottom of each column and say, does this do something? When you look at all of these, you're essentially doing a hypothesis test on each one of those. So now the question is, well, what if the null hypothesis is not true? What if it's not 0 and the null hypothesis is, or the mean of the effect is over here at 8? And again, if you remember from chapter 6, we assume the noise level hasn't changed when we ask this question. It makes sense to use the same one. So now we want to figure out, that's the power of our design. Does everyone buy that? So E star was T star times SE. So 2.120 times 2.8. What do you get there? 5.89. Where is it? Did you get anyone get a t value? What'd you get, Katie? Negative 0.76. So 5.89, that corresponds to, and then the probability, you look up 0.76 in the table with 16 degrees of freedom, and let's see, so the table value is, you get a table value?
Oh, yeah, you mean if in conversion of the beta to the
Okay, so the answer is 0.75 to 0.9 for a, and that's the power, not the beta, right?
yes, because the beta was between 0.1 and 0.25.
So beta here was 0.1 and 0.25, somewhere between there in the table. So 1 minus that is the power. So somewhere, if we had a table that had more numbers, we could get that a little bit more precise. But the power of our experiment is between 75 and 90% of detecting an effect that is that size of 8. Anybody get fairly far along this path of power? People here? Some other people thought. So if I throw that at you on an exam, you'll do much better than the last time that happened, right? don't want to risk the sadness that might happen after that. Okay. So again, it's a tough problem because it's probably the toughest concept from chapters 1 through 6, kind of integrated with lots of new stuff anyway. But keep in mind that concept of power is pretty important. So if an effect of size 8 means that wow, that's a really big change in yield, we would really want to detect that, then we could look at this and say, well, our experiment is pretty good. It has a pretty high power to detect that degree of difference for an effect, that size of an effect. Okay. Any questions on that? All right, that was a lot of fun. This is another example. Let's jump over that. We've done a lot of these examples. And let's move on to the next section of notes. Hit the wrong button. Those chapter sections that's a different book, sorry about that. Now what we're going to be doing here is just adding a few more bells and whistles to our full factorials. And some of these things are really important. So the first question, how do we know that we did enough experiments? That's directly related to this power question we just asked. So if, say, in that example we just did, if I said an effect this size, let's say this is an effect of size 8, if that's really important for us to detect, that size of an effect, then we better have enough replicates so that that will show up as significant. Or said another way, our experiments will have a high enough power that if an effect is of size 8, it will show up as significant. So that is a question of power, and really that's our main adjustable parameter in a power calculation is how many experiments are you going to do? How many replicates of the design are you going to do to get that level of power? And we'll go through that fairly quickly. We already did this. I moved this into the viewer section of the notes, so good for you. You've got all that done already, or that part of it you've got done. Then, before we do this, we're going to learn another statistical test, a test for curvature. As I think Aiden asked last time, how do we know that the linear model is okay? And I didn't answer directly because we got to learn a procedure that says we better test that. We've assumed that a linear model is okay. We assume that if we looked at x1 or x2 or something like that, if we only have 2 data points, we can only draw a line through those. And how do we test to see if that line should be something more than a line, should be a curve? Then lastly, we're going to learn a lot more about blocking, which the one run-in that we've had with blocking was with our paired t-tests from before, in which we were trying to block out some source of variation. We're going to look at how do we do that, how do we expand that and do that a little bit more and be able to block out sort of multiple sources of error. All really good things. So let's first start with this question of precision, or a question of how many experiments do I need to do to have a decent power. And looking over the notes, I think there's a more straightforward way of talking about this, and I'm going to attempt that now. So I think I can go through several pages of notes with just one sort of explanation. We just did this power calculation. Every time we're testing if an effect is significant, we're assuming the mean of that effect is 0. And we've calculated some noise level, which is SE. We do a two-tailed or two-sided hypothesis test in which we find some rejection region. Remember that? And the cutoff region, I could write this in terms of a T star or an E star. So just different units. So remember, T star is E star divided by SE. So E star is that. So E star is just how big of an effect, how big does the effect have to be for us to say that's real. That effect is doing something more than the noise. And it's when an effect is either much larger than 0 or much smaller than 0. And well, where do you cut that off? That's the borderline, this E star. Is everyone okay with the idea of that hurdle value? Okay. So then we just can look at one side of this. It's true for the other side as well. If we want to say, I say this a lot, I say, if an effect is this size, will our experiments detect it? And what I mean by that is, if an experiment is this size, will our experiment have a high enough power to show that it is significant? So I'm going to replace the words this size with the Greek letter delta. So if the null hypothesis is not true, if we have a mean effect that is some size, delta, and so that's a number like we did before, like 8. And where do we get that number? That is from just practical experience or the economics. In the reaction yield example, we'd say, boy, if an effect would change the yield by 8 points, that's huge for us. That's something we want to know. That's where we get delta from. Delta generally comes from, we could lump it all together and just say, the economics. I mean, sometimes we calculate delta. That's reasonable too, but somehow some practical bit of information says this is the size of an effect that we think is important for us to detect. And so we want to detect that with a certain power. Okay, so now we're going to get really imprecise here, a real rough calculation. If alpha is 5%, then that t-value is going to be about 2 standard deviations away from the mean. Plus or minus 2 standard deviations to the mean captures 95% of the data. That t-value is going to be around 2. Does everyone agree with that? About. Likewise, this one won't be exactly 2, but we would say that distance is, roughly speaking, about 2 more standard deviations. And that would give a power, that would give somewhere between 2.5% or so. This is rough because we're talking t-values, not z-values. We're not talking about degrees of freedom here yet as well. But if we want an alpha of 5%, so a type 1 error of about 5%, and then a beta error of about, on that order of 5%, we're looking at both those distances being 2 standard deviations away. So the total difference is what? Who's got 2 plus 2? Who wants it? 5. Almost. Who wants 2.2? 4. Okay, we're not gonna do this again. So 4 SE. That's the total distance, and that is delta. So what's that saying? That is the development of about 6 pages of notes, but I think this is a lot better because it's clear. I hope. All right. So everyone see that? That's a rough way of figuring out that we should be able to detect an effect of this size. Now, we know SE, right? We know SE is 2SP over the square root of NF. 2 times 4, not just going to do it myself. That's what that equation comes from in your notes. Let's just solve for NF. But replace all this business in your notes with this. All right, I would write delta equals 4SE. And I would memorize that because I think it's a very, very practical thing to know. So in that last problem, we could have calculated SE, and then we just say, all right, 4 times that number, that's the size of delta that I have a pretty high power to detect. You have a very rough feel for the size of an effect that you can reliably and repeatably detect. all you have to remember then is this, which hopefully after a long time of doing homework and group problems, that's there as well. So we can use that equation then. We can figure out how many experiments should we need to do if we know the noise in the individual measurements. Now I admit that when you start off an experiment, you don't always know the noise in your individual measurements. And very often, one of the first things that we do is, before you do a bunch of experiments, is to try to get a little handle on SP. So let's do this group problem. Let's do parts A through C. By S there, we've been calling it SP. That's the standard deviation of individual measurements. Central limit theorem is still number one by Harps. This is number two. Remind me to talk a little bit about that. Why this is and then when you get done with parts A through C, think about Morgan's question. What is K? You can go through the calculation without really thinking about it, but that is a good question. you guys get 23 in that calculation? But is that the answer to the question, though? No. What's the answer to the question? You wouldn't go tell someone run a 2 to the 3rd factorial with 23 runs, would you? Right. You run 3 replicates, so NF has got to be 24. So a 2 to 3 design, it comes in units of 8, right? 1 replicate is 8 runs, so we have to have a complete, set of experiments. So that's why we can't run, well, we could run 23 experiments, but we would be doing ourselves a great disservice of leaving one out. So in this case, we would have to run, we'll say, 24 experiments. 8 times 3, 24. Does everyone get that? If we did the same thing, don't want to get ahead of myself. Most people got this done, I guess. The calculations, like all parts of this, that didn't change, right? But in this case, if we have a 2 to the 4 design, how many replicates are we going to run? 2. So that's 32 runs. So now we think, all right, K has something to do with this. And part C shows sometimes K doesn't have a whole lot. Very often we use this equation backwards. Very often we have a certain budget that we're dealing with, which says I can only run this number of experiments. And we can back out a delta, which would be if I can only run 16 runs, then this experiment is reliably detecting effects that are this size. And then you would compare that with, is that huge? Is it small? Somehow you compare that to the real world. So we get a delta of 30. So that means that if an effect is of size 30, you're going to pretty reliably, you can be pretty safe that your experiments will detect it, which means it will show up as significant when you do your experiments. What about this question? Does that answer depend on K? No. There's no K involved in the calculation. So whether, in this case, you could have run a 2 to the 3rd design with 2 replicates, or you could have run a 2 to the 4th design with a single replication. And as far as this precision goes, it doesn't matter. If you think about an effect is an average of high minus low, there's still 8 runs going in the high value, 8 runs going in the low value in both of these cases. Now, of course, it matters on how do we calculate SE and those kind of things, but for this precision calculation, it doesn't matter. Yeah.
Unless K in this case would be 5 or above.
Right. Unless the packets of experiments change. Yes. So unless you have problems getting a complete design like we did before. But the point of it is the precision is really based on the total number of runs. So why is this so important? And when you hear anyone criticize this statistical design of experiments, they'll say things, and I've had PhD friends that generally, so these are people not here, generally at UND, collaborated a lot with chemists that didn't really learn DOE stuff, and they would say, oh yeah, I recognize something of statistical design of experiments. It takes a lot of experiments. They require a lot of runs. So there's a misconception that somehow they're inefficient when the opposite is true. They are the most efficient runs. That's one thing. The other part of this is very often, if you don't know this very simple equation, and don't go through this calculation of either I know my budget and I'm going to calculate a delta, or I know my delta and I'm going to calculate number of runs. If you can't do that before you start, what happens is people just jump in and say, all right, I'm going to do a 2 to the third design, I'm going to do 2 replicates, and if they don't go through this, they might, what happens a lot is that their experiment has such a low power because there's so much noise, is they're only going to detect these gigantic effects, which if they're that big, they probably already know about them anyway. So they spend all this money, they have all this time, and they do these experiments because they didn't do this calculation beforehand, and they find nothing. And then that's a really bad place to be in to present, I just wasted a whole bunch of resources and I didn't find anything, right? Because somehow this was my project and I thought this was a good idea and I pushed it and we got nothing out of it. And so that's where you do this before you launch into any experimental campaign, which means that probably your first priority is either you have some existing data or you take a few points to get a handle on S, right? That's just a standard deviation of individual measurements. You might just take 3 or 4 points at the same condition to get a ballpark of S. Then you do this calculation. You decide, is it worth doing this whole experimental campaign, or do we stop now because, say, that S is way too big and we need to focus our efforts on reducing variability? So then you can be effective in using this stuff. Otherwise, it happens so many times where people jump into this and then crash. One other practical thing, and this is a grad student of mine. So my stories that I love to tell are stories like this. I gave someone advice, they didn't listen to it, and bad things happened. So those are my favorite stories. That's sort of all my stories have that same theme going on. So it's the same story. So my grad student, Steph, she was going to do this big factorial design, huge one. And I said, make sure you can do all the experimental conditions. Make sure you can physically set all these at the high value and get a result before you start doing it. She's, no, I know I can do it. I know I can do it. And we all know what happened. She got about halfway through the design. She tried to run one condition and it failed. She had to scrap it and start over and pull in her -1 and +1 values to something that she could actually do, and then start over again. So that is such a huge waste of time, but it provided me with a great story that I can say to all statistics classes, so that is a happy outcome. We have 2 minutes. Let's hear your questions. Chris had a question?
No.
John had a question.
Are those people that had those questions, are they still your friends?
Are they still my friends? I'll call them friendly acquaintances. How's that? Anyone else? Good question. Kind of, sort of. All right, so I'm letting you guys 2 minutes early today. 2 minutes early. See you Wednesday.